Hey everyone, and welcome to The Explainer. Today, we are taking a deep dive into what is honestly the biggest headache in modern AI deployments right now. I'm talking about agents with goldfish memory. We're going to look at the massive architectural shifts that are finally transforming AI from these stateless, forgetful bots into complex systems that can actually do lifelong learning. So let's jump right in. This quote right here, it hits the nail on the head. Our underlying models have gotten unbelievably good at reasoning. But if you try to reason without the right historical context, well, that's just expensive hallucination. Memory isn't just some nice-to-have feature you can bolt on at the end. It's the fundamental building block that makes everything else actually work. You might be wondering, why do autonomous agents actually fail the minute we put them into a real production environment? If you've tried deploying agents, you already know the stakes are super high. They fail because they literally can't remember yesterday's conversation, they can't pull the right context from your docs fast enough, or worse, they just confidently spit out false rules they hallucinated 3 interactions ago. If your agent can't maintain its state, it just can't do complex work, period.
So here is our game plan for today. We're going to cover why basic memory fails, break down the 4 tiers of AI cognition, look at OS-inspired models, dive into graph architectures, talk about strategic forgetting, and wrap up with the top deployable frameworks. All right, part 1, why basic AI memory fails. For the longest time, the go-to move was just dumping raw text into a flat vector database and calling it a day. But at scale, that leads to 4 catastrophic failures. First up, context poisoning. This is when an agent stores a hallucinated fact, like a fake refund policy, and then retrieves it and repeats it later, completely compounding the error. Then you have context distraction, where the database spits back 10 irrelevant results and the actual signal gets totally lost in the noise. Third is context clash. Imagine retrieving a user's old address and new address at the exact same time. It's a mess. And finally, work duplication, where multi-agent systems just endlessly repeat tasks because they don't share a state. Moving on to part 2, the 4 AI memory types. To actually fix these failures, we have to stop treating AI memory like a dumb database and start treating it as a multi-tiered cognitive architecture. Tier 1 is working memory. Think of this as the agent's active workspace. It's basically the AI's RAM. It holds the current conversation and whatever immediate tools it's using, but it's hard capped by the context window. It's lightning fast, but it's temporary. Once the chat is over, poof, it vanishes. Next up is episodic memory. This is the timeline of specific past experiences. It tracks exactly what happened. This is the magic that lets an agent preserve continuity across different sessions. So it can remember exactly what you guys were talking about last Tuesday, which makes the whole interaction feel seamless and long-term. Then we have semantic memory. While episodic tracks what happened, semantic memory tracks what is true. This is the persistent, hard knowledge base of facts about the world, the specific domain, or even user preferences. It effectively grounds the agent in a library of external facts that can be updated continuously. And the 4th tier is procedural memory. This is where learned skills, rules, and action sequences get encoded. Say an agent figures out a really complex workflow, like authenticating a tricky API. It stores that knowledge right here. That means the next time it needs to do it, it just executes the verified workflow instead of burning massive amounts of expensive tokens trying to reason through the whole thing from scratch. Part 3, biological and OS memory models. So how are researchers actually building these tiers? Well, there's a really sharp contrast between the 2 main paradigms. Down at the bottom, you've got parametric memory. That's the rigid, baked-in knowledge stuck inside the neural weights from training. It's a black box, and it's incredibly expensive to update. But on the top, that's contextual memory. This is the external, highly flexible memory we are obsessing over today. It lets agents pull dynamic docs, visual data, and historical context on the fly without ever retraining the underlying model. Building on that contextual approach, researchers have come up with OS-inspired frameworks like MemGPT and MemOS. And they use a brilliant analogy, memory paging. The AI actively manages its own context by literally paging data. It keeps the immediate stuff in short-term core memory, again, like RAM. It summarizes recurring topics in mid-term memory, and it shoves the massive archival data into long-term disk storage. The LLM itself decides when to swap data in and out. This approach can literally slash token costs by up to 90%. Part 4, hierarchical and graph architectures. Okay, so how do we organize all this external data so the agent actually finds what it needs? We already know flat vector storage relies on fuzzy semantic similarity, which honestly just grabs a lot of irrelevant noise when you scale it up to millions of memories. Enter hierarchical memory, or HMEM. Instead of scanning every single thing, HMEM routes data precisely. First, it hits the broad domain, then the specific category, down to the trace, and finally the exact episode. It's like reading the label on a filing cabinet drawer before you start rummaging through the folders. It totally prevents context distraction. And you have to understand the difference between standard vector RAG and graph RAG. Let's say you're building a medical AI. Vector similarity might tell you, drug X treats high blood pressure. Great. But it might completely miss that drug X interacts lethally with another medication the patient is taking. GraphRag fixes this by mapping out explicit multi-hop relationships. It travels down a verifiable path of nodes and edges. When you're dealing with life or death or just strict facts, you need that exact grounding. Fuzzy vector math is just too dangerous. And when you get this architecture right, the performance gains are just staggering. 31x. That is how much faster the new hippocampus memory model is at retrieving data compared to dense vector databases. By using something called a dynamic wavelet matrix, it compresses and co-indexes both semantic signatures and the exact token streams. The result is ultra-fast, highly scalable memory search that is absolutely perfect for long-running autonomous agents.
Section 5. Strategic Forgetting and Consolidation.
Now here is a wild concept. Having unlimited memory is actually a massive liability. If you never prune your data, your agent's memory just turns into a noisy, chaotic landfill. To fix this, agents are starting to use an active dreaming protocol. It's literally just like human sleep. The agent goes into an offline sleep phase. It reflects on all those raw episodic memories from the day, like API timeouts or auth errors, abstracts the root cause, and generates a brand new procedural rule. Then, it safely deletes the noisy raw data. The AI is actively learning from its mistakes, which means strategic forgetting is absolutely essential.
Finally, Section 6. Top Agent Memory Frameworks.
Let's get practical and talk about the tools you can actually deploy right now. The secret here is picking the right framework for your specific problem. Mem0 is absolutely fantastic for personalization and consumer chatbots because of how it handles self-editing, scoped memory. Zep is going to be your go-to for really long-running sessions using this cool hybrid vector and temporal graph approach. If you're already deeply invested in the LangChain ecosystem, LangMem is great for updating procedural rules. And Letta, which used to be MemGPT, remains the gold standard for complex autonomous agents, with that OS-inspired tiered memory we talked about earlier.
Continuing with our frameworks, if you need a totally offline, privacy-critical setup, Cogni is amazing with its local-first Graph Polystore. For all the enterprise folks locked into Microsoft, Semantic Kernel gives you Azure authentication right out of the box. And then there's Supermemory. This one is incredibly powerful for high-speed agentic workflows because it integrates directly with MCP, the Model Context Protocol. Now, why does MCP even exist? It's here to solve the massive interoperability nightmare in AI. Think of it as a universal, highly secure transport layer. It uses a standard client-server architecture. Your AI hosts, like your code editor or your chat app, act as clients. They seamlessly connect to remote MCP servers, and those servers securely expose specific resources, executable tools, and standard prompts. Because the communication and transport are entirely standardized, you don't have to write custom code every time you want your agent to talk to a new database or tool. MCP handles all the routing, security, and authentication for you. So in the real world, this means an AI coding assistant can securely read your local files, ping an external GitHub repo, and hit a remote memory server all in one continuous session. You get sub-300 millisecond access, giving agents persistent context without developers having to pull their hair out writing custom integrations. It's a total game changer. So to wrap this all up, moving away from simple, flat vector databases into multi-tiered, hierarchical, and graph-based systems is really the only way we are going to scale AI effectively. Memory is a strategic architectural choice. It's not just a storage bin you tack on at the end. As we start deploying agents that can actively page their own context, consolidate rules while they dream offline, and strategically forget the noise, it brings up a pretty massive question. What will your AI choose to remember? Thanks for hanging out with me for this explainer, and I'll see you in the next one.